Is it working now?
Yeah.
Yeah, cool. Okay. So yeah, welcome back. Do you have any questions regarding last time or something that came in between? So we had been discussing interior point methods last time, and we got in the end to this algorithm. That's basically the prototype algorithm for a primal dual interior point solver. That's what most solvers are doing when playing with interior point methods. We can maybe go through a little bit the idea again. So you have a bunch of, if I backtrack a little bit, a bunch of KKT conditions to solve. We had this essentially. This would be the primal dual interior point KKT condition, so the stationary Lagrange function primal constraints. Then if you remember inequality constraints, we introduce slack variables, and we say that h plus s must be 0, which means that s should be larger or equal to 0. It's like kind of filling the gap of h to 0. And then you have the complementary slackness conditions, mu I times si. So you have a list of products like this that should in principle be 0. But if you set them to 0, you have this corner that Newton does not like. So we disturb this condition a little bit by subtracting some barrier parameter, often labeled tau. That relaxes this corner into something roundish that we can control. So we can make it more or less smooth and more or less accurately approximating the corner. And then all these methods are about applying Newton on this system. So we had this picture here where we were like solving the equations to full convergence, then reduce tau and do that again. And we discussed that this was not very efficient because you're basically solving a problem that you don't care about. For example, here, if you solve to full convergence for tau is 1 in that case, you land on that point, but what you're targeting is that point down here when tau is very small. So there's no point in trying to converge too much the equations here. And so the idea was to update the tau a bit faster as the equations are converging, which was looking like this. So a few iterations. And when you see that you're kind of close to this central path, you remember that's basically all the solutions of the primal dual KKT conditions for tau is 1 to tau is 0. So that's really this thing that we're trying to follow with these methods. You reduce tau on the fly every time in the equation. So this residual here looks good enough, and that allows us to converge much faster. Maybe I can comment a tiny bit on the theory behind these methods, because people prove that they converge, and they mostly prove that they converge if you do things in a very conservative way. So if you reduce tau only when you have like really converged the equations or close to that, and in practice they reduce tau much more aggressively. So you have, if you read papers, you would see the distinction between short step and long step methods. So in practice, solvers cut corners and it works, but in theory you cannot, supposedly cannot reduce tau very fast. And yeah, that was the end point. You can essentially write a code that looks like this, and so you need to evaluate all the elements that are part of your primal dual interior point KKT conditions. Then the Newton step looks like this. You had this matrix that has this very specific signature, if you want, or pattern. So you have the Hessian gradient of the constraints, lots of zeros, identity, and then some diagonal matrices that contain S and mu. So you compute a Newton direction that comprises primal and dual variables and slacks. And then you need to step size a little bit. First, you need to step size such that S and mu remain positive, and are like classic tricks that they cannot reduce to less than a fraction of themselves. Like epsilon could be like 0.1 or something like this. And then you also need possibly to reduce a bit more from that to make sure that you're always progressing on your equations. And then when the equations are solved enough, so if this thing here, this norm is small enough, then you reduce the tau and keep going. And so codes like IPOP, they essentially do that. And all the development that comes on top of that, it's about like heuristics to make sure that things go well on the way, essentially. But the basics is not very complex. Right? So we discussed that last time. I also showed you some an example here that was an Mpc example, just to show more like in practice how the solver will treat a problem. And we had here, there was like a very, very coarse plane dynamics, like moving in 2D, so no altitude, and you have a bank angle, that will be the theta, that you can use to like turn. And no, sorry, theta is the orientation, theta is the heading, and phi is the bank angle. And you can control the velocity as well. And yeah, just to show you that in principle you can solve problems doing very like basic things. For example, here I'm discretizing the dynamics via a simple Euler integrator. We discussed integrators and very advanced techniques to process the dynamics. But if you need to go quick and dirty, so to say, or you don't care too much about efficiency, this kind of things can work very well and be very easy to code, for example. So in that case, I'm really taking these simple steps forward. I impose some restrictions on my velocity and on the input. And then I had this extra constraint, which was kind of creating an obstacle for the plane to avoid essentially this red thing here. So you could really think about how should I avoid some obstacle with some maybe some backup for safety. And then I was showing you the iterations that interior point methods would do on a problem like this. And you see that the tau is large at the moment, it's about 1. And what happens in practice is it's an interior point effect. So the solution, when you solve at a fairly large tau, will basically be rejected deep inside the feasible domain. And in our case, it's maybe a bit upside down, but this is infeasible. So the feasible domain is outside this circle. So being rejected out or inside the feasible domain, that's basically being pushed away from that obstacle. And so it converges a little bit the equations, and then it starts reducing the tau. Now tau is 0.1, so it's coming closer. And you see that here at 0.1, you're still kind of a bit pushed away from the obstacle, but then as you reduce tau, you can pretty much visually you touch it essentially. Right? And then we can go MPC style on this, which means you compute this trajectory, the plane will be here, initial conditions, and then you just apply the first control move, so the controls would be here. And after one sampling time sample, you would recompute everything based on the latest state estimation. And then you would have an effect like this. Right. So that's typically the kind of things you may want to do in your projects, like doing some MPC-like things on a control problem. Okay with that? Yeah. Okay, this matrix, we'll see it again in a little bit when I discuss QP solvers, but we can look a little bit at what it looks like in terms of sparsity. So these are the non-zero terms. You can see that it's almost symmetric, but not exactly, because of these two terms here, and they don't exchange. But the sparsity pattern is symmetric, and this is identity, and that's the matrix that is diagonal. So visually, it looks symmetric. And that's the signature of this kind of matrix. For the control problem, we just saw like the plane problem. So that's pretty big, but it's essentially full of zero. All the the white stuff is zeros, and you have the Hessian here, it's block diagonal. You have this dynamic constraints. That's basically my Euler integrator being like stacked into the constraints. They are not block diagonal, but are banded. These guys are block diagonal. It's not obvious from the picture, but that's what they are. And then you have these three lines here, which are these three diagonal matrices. So it's really purely elements on the diagonal. So even though this matrix is very big, it's typically fairly cheap to factorize or to essentially solve this linear system if you exploit the fact that you have lots and lots of zeros. To get that ordering, you need to order the variables and the constraints in the right way, which is essentially time-wise. So you would have the variables, the W would contain x0, u0, x1, u1, and so on, all the way to the end. And the constraints would go in time, so that's the initial conditions, and then the first shooting gap, second, and so on and so forth. Then this pattern follows naturally. So I'll show you in a bit later how you can treat this kind of matrix in terms of linear algebra, because there are ways to do that very efficiently. If you call IPOpt, IPOpt will not do anything very special with this matrix. It will just throw it at some LAPACK library that you can actually choose in the options, and the magic will happen down there. And typically these libraries will analyze your matrix, spot the non-zeros, and devise the pivoting to organize things in a nice way. Okay. Now, one thing I wanted to discuss briefly here, and it's kind of related to this NMPC problem I'm solving using interior point methods. So when you solve an NMPC problem, like for example this plane thing here, what you can see in some sense is that you're essentially solving all the time the same problem, so to say. Here I solve a complete optimal control problem and I get this solution. But if you think about it, if I was, the next problem will be this one, right? I move a little bit in time and I'm gonna solve a new problem here. And if you look at the solutions, what really happened is not much. So essentially, if I could start my problem from the second sampling time here and use these guys as solutions all the way to n-1, I'm skipping one timestamp here, they would be close to optimum. Right? Does it make sense? Yeah. So in some sense, once you've solved a problem once, the next problem is very, very similar to what you had before. You need to fill one timestamp in the end. So basically decide what will come at the last time instant, because you don't have it yet. But you can make pretty good guesses about that. So that's one source of changing a bit the solution. And the other source would be if you have disturbances on your system. So if the trajectories are not doing exactly what the model was predicting. But if things go well and the sampling time is pretty high, and if you don't have massive disturbances in your real system, you're essentially solving the same problem over and over again. And so obviously there's something to do about it. If you have something that looks almost like your correct solution, it's a good idea to use it for your next solution. And when we do that, we're talking about warm starting essentially. So I already have a pretty good idea of what the solution should be, and I want to use it for solving the next problem. Does it make sense what I'm saying? Yeah. Now I want to tell you a little bit what happens when you try to use that in the context of interior point methods. And that applies to all interior point methods. I'll show you for the primordial style, but if you use barriers in the cost function, these things, it does not change really what happens. And to see this, we can backtrack to this very simple problem that we looked at last time. So you want to, you have a minimum down there, and you have a quality constraint that would restrict your solution to be within that ellipsoid. So that was the primal view on the problem, and the dual view was here, so that's the mu, and you have the slack variable here. And so the central path is here, going down to there. So that would be, if you solve the Kigali conditions for tau is 1, so large tau, and as you reduce tau, the solutions would move down here. And that's the, like as close as it gets, the true solution of the problem. And in that space, you would start here at tau is 1 and move down this manifold down to here. And you see that you have an active constraint. S is 0, it's scalar in that case, only one constraint. So S is 0 and mu is slightly non-zero. So your solution is pushing a bit against that constraint. Okay, but let's assume for a second that we actually have a good initial guess for that problem. For example, let's say that I feed my algorithm with this W's. So I'm pretty close to my green solution, right? And let's say that I will feed also my algorithm with this mu here. So it's very close to the true one. And with S is 0. So in principle, I'm almost at the solution. So I could hope that my algorithm will use this thing efficiently and converge very fast. But if you do that and apply the algorithm like kind of naively, so you start with tau is 1 and you reduce it if you see that the equations are small enough. The problem is that your solution will backtrack all the way here, right? Because for large tau, the equations should shoot for this point here and that point here. So Newton will actually not like this point. He will say, no, actually, for me, the solution is up here. That's where I'm going, right? So take a step up here, and there, actually, you're not very far from the central path, so the algorithm will reduce tau, and then start going down again towards the green solution, so down the central path, right? You got that? Yeah. So what's happening here is essentially, even though we started from a very good initial guess, the interior point algorithm actually went back home in some sense to where tau is large and then comes back. So you have this effect of retracting into or along the central path before going down. And on this picture here, you see how the equations are behaving, so reducing, and how the tau is also behaving. And that's the step size on your primary dual solutions. So you have this effect of retracting inside the feasible domain before going back to the constraint. So what can we do about this?
Start with small tau?
Yeah, we can try that. So what about trying to keep tau low and see what happens? So we can do that. For example, here I'm zooming a bit in this mu and S space to see a bit more what's happening. So I'm starting from same point as before, and I actually use a very, very small tau here, 10 to the minus 10. And I'm trying to step to my solution. And well, indeed, it seems to work pretty well. Newton shoots right away at the correct solution and converges very quickly. Okay, that looks good. But that's not the end of the story. Here is another attempt with also a tau very small. Solution is very close to what it should be, but let's imagine for a second that I got the active set wrong. So I thought, using the previous solution, that at this point the constraint is not active, so S is non-zero and mu is 0, right? And unfortunately, maybe some disturbance happened in between my previous solution and now, and now the constraints become active. So I should move this point from here to there. And so I'll try my tau very small. And the problem here is that, well, Newton will shoot down here, and well, up here is going there. And now because tau is very small, I have a very, very sharp turn here on my equations. And Newton will have to deal with that. And it actually manages on this problem, but it will spend a number of iterations. You don't see anything happening, but Newton is basically trying to take this very, very sharp term. And it's not liking it so much because it's so sharp. So it has to take very, very small steps to navigate that corner. So it's staying here for a number of iterations. And once it clears the corner, then it can shoot for the points and converge there. And you see here Newton struggling with that corner. Here it took only 3 steps through it. That's actually really fast. It's often much slower than this. And then it can take full steps. So that's a Mickey Mouse problem. On serious problems, going through corners like this, that's not gonna be easy at all. So if you try to do that, like you believe that you have a very good initial guess, and you try this gamble, take a very low tau, you may have problems with this navigating the corner. So it's only a partial solution, and here I'm showing what happens with this Mpc example. So that's the plane, and that's if I apply the algorithm naively, so that's with reset. So I put tau back to 1, so I need to retract to the central path, and without resetting the tau, so I keep tau low. And what happens, this is the result of the equations at each time instance. So each of this curve is one instance of solving the NMPC, right? So it's starting with possibly high R, and then it's collapsing them. You understand this picture? Or should I? No? Okay. Whenever you solve your NMPC scheme, you have a new problem. Huh? So you start with the equations being not fully solved, and then you iterate, and they would be solved after a while. Right? It's the classic picture with these dots that go down, and that's 10 to the 0, and that's maybe 10 to the minus, I don't know, 8 or something. Well, I have 10 here. So it's a semi-log scale. So we have the iterations here of the method, and is the problem solved essentially? When a norm of R is very small, you're solved. Is it clear like this?
What's done without reset?
Right, okay. So we just discussed 2 views of warm starting. So you just throw your guess at the algorithm, and you just run everything naively. So the algorithm will try again with tau is 1, and then decrease when possible.
And with reset is resetting tau?
Yeah, that would be resetting tau. And if you don't do that, like keep tau very low, that would be the red one. And so there's good and bad news. The good news is that when you don't reset, so you keep tau very low, on some instances it converges very fast, and on some instances it's slow, and on some it's very long, right? And so you really have this effect. It was probably here no change of active set, so it was converging really fast, and if you have to change the active set, you'll tend to be a bit slow and land here or even slower. Whereas if you reset the tau, then you have a fairly uniform convergence. Well, this one is a bit slow. I'm not sure exactly what happened there. So yeah, if you reset the tau, you will need a number of iterations, but at least they are somewhat predictable. If you don't, it's unclear how many iterations you will need. But the bottom line is that warm starting in 3-point methods is not easy. And people have looked at this problem for a number of years now, and there are some decent attempts, but there is no magic solution. it is a bit of a difficulty to deal with this trade-off, large or small tau. Okay with that? Okay, I'll soon conclude, but I wanted to show you one view on this, because so we have looked at point solvers now, and we have looked at SQP before, and actually if I look at this box, I have point QP solvers here. And as you may suspect, and we'll get to that, but essentially here we're talking about using these methods on QP problems, simply, right? And one interesting thought, and that's something that's not everyone fully understands, I guess, is how is it different to use an point solver directly on your NLP, or go through an SQP strategy that relies on point QP solvers? Because if you do, for example, real-time NMPC, you may have to choose between these two different paths. Either you deploy an point code directly on your problem, or you form an SQP in which you solve the QP solver, possibly with an point method. And I'm trying to see a little bit what happens if you do that. So it's not very deep, but just to get a sense of what's happening. So that would be an SQP code, prototype of that. So you basically form the NLP, so classic discretization of the OCP, maybe using multiple shooting or collocation. You get an NLP, and when you solve the NLP using SQP, so you need to form all these terms that will basically build your QP problem, and then you form the QP. So you have the Hessian of the Lagrange function, gradient of the cost, linearization of the constraints. You will solve the QP and then update your primal dual variables and do that again, right? Remember that approach? And you can imagine now that in order to solve that QP, you would throw the QP at an point QP solver, which would essentially do Newton steps on the relaxed primal dual KKT conditions of the QP problem. So if I write the KKT conditions associated to this guy, and then I relax the component slackness conditions, essentially I'm talking about iterating these equations on Newton while reducing tau. All this art we have seen before on the QP problem. We'll discuss more about doing that in a bit, but hopefully you get a little bit what's happening there. Now on the contrast side, what if I was throwing an point code directly to my problem? Well, what I would be doing then is I would form these terms, same as here, and then I will take a Newton step on the primal dual relaxed KKT conditions associated to the NLP directly, and then update my primal dual variables accordingly. That may be clear or not, but when I form a Newton step on these guys, this linear system I will solve will actually be the same as this one at the end of the day. I would linearize these equations and take deltas on all the variables, and I'll end up essentially doing the same thing here, roughly speaking. So at the end of the day, if you do these two different things, they are not that different. You kind of solve the same equations and do the same things. There's one difference though, which is in this case you form these linearizations once, and then you do a number of iterations. You converge as far as you can your equations on that linearization. On that side, you don't converge so much. You reform this linearization at every step, right? You form that, take a step, form again, take a step, form again. Right? So here's the comparison. If you do this approach here, you would form less linearizations of your equations. You'll form that once and then do a lot of work with that. And a lot of work, by that I mean you would do a lot of linear system solves. So you would solve these linear equations a number of times, updating the tau throughout. On that side, you do one factorization for each generalization you're making. So here you're kind of sharing the workload between these two guys a bit more. Then about the warm start, that's a big difference. On that side, actually, it's quite effective to warm start this method. It's an SQP, it's easy to warm start. The warm start will not be good in that loop, but in terms of the outer loop, it will be good. And this guy will kind of deal with the active set changes, and this one is not easy to warm start. On that side, it's not easy to warm start at all. Okay with that? So you can try to have that picture in mind when you make choices in how you solve your optimal control problems. Yeah, and remember that at the end of the day, the work that is done inside the computer is not that different on one side or the other. Then there's what will really happen in the end will depend on the codes you will be able to deploy on the problem. Okay with that? Yeah? Cool. Yeah, I guess we should... no, okay. You take a break a bit later. Yeah. Let's can get started with that one. Okay, so yeah, I should talk about QP solvers a little bit, because there's also quite a few interesting things there. There's still a bit of research development on this QP solvers for direct optimal control, but I would say that most of what can be done for classic problems has been explored in the last 5 to 10 years, I think. So now we are going for these boxes here. So I kind of already told you a little bit what's happening in there, and I'll show you what happens in there, and I'll also show you some other things. All right, so let's talk about these guys. Okay, so if we go back a little bit to the big picture. So at the end of the day, we're trying to solve optimal control problems, which will have this kind of structure. So you have a stage cost. You typically sum these contributions over the different discrete states and inputs. You may have some terminal cost, and we have, if we do something like multiple shooting, this kind of constraints to hold in the problem. And this kind of inequality constraints, they may change over time. Yeah, that would be a multiple shooting approach to discretizing the problem. So before that, there's all the artillery of multiple shooting and forming integrators and these kind of things. Then if you do SQP on these things here, you'll end up forming these QPs here that we discussed before. So maybe you will order your variables like this, and then the Hessian of the problem appears here. Gradient of the cost, so the cost is basically this complete thing here, that's the phi. The G would collect all these constraints here from k equals 0 to n minus 1, and the H would collect all these guys here, right? It's a classic picture. And now here is a bit of a primer. The bottom line is that depending on the problem you're trying to tackle, it may make sense to use different approaches and different codes to solve the QPs in the end. And there's a number of things that enter in selecting the right approach, and it's not always obvious how to do it. Sometimes it's easier to just benchmark, but it's good to have an idea of what may impact your choices. So a bunch of points. So the problem may be small, medium, or large scale. By that I mean the number of states, the number of inputs, the horizon length, and so on and so forth. The horizon that you're trying to use, so this n, how far ahead in the future you're looking when you solve your problem, it matters actually. If it's short or long, it may make you choose different codes. The type of inequality constraints you have, that can also impact the techniques you want to use. So if you have simple bounds, or if you have like complex polytopes, or even something worse, like for example quadratic constraints, or some like fairly complex convex constraints, or even non-convex ones, that may change how you want to do this. The ratio between how many inputs and states you have in that problem also matters, and even the question whether your dynamics are stable or unstable will also have an impact on how good different approaches will be. Okay, so I'll try to explain a little bit why all these things happen. So you can try that. And I'll mostly talk about these two approaches, active set versus interior point. There are other techniques, typically first order methods. Now you have all these ADMM techniques and decomposition techniques that have also some interest and advantages, but I'll stick to these ones here. Okay, so active set method. Essentially, what will happen there is that we'll try to identify the active sets in the problem. And as we will see, essentially, if you know the active set, solving the problem is trivial. So the idea of these methods is to try to pinpoint what active set is currently operating in the problem. Okay, so what are the KKT conditions associated to that QP here? So again, now we have the discretization of the OCP resulting QP. And if you write down the KKT conditions here, you have here the gradient of the Lagrange, Lagrange function. So that thing here, that's the contribution coming from the cost. And then you have the contribution coming from the scalar product lambda g and the scalar product mu h. And you take the gradient of these things, you end up with these terms here. And the rest as usual, so the constraints, equality and inequality, they just come in as primary conditions to satisfy. The mu should be positive, and then you have the complementary slackness condition. So mu and h cannot be non-zero at the same time. So this inequality constraints and the mu cannot be non-zero at the same time. So the classic stuff. Now let's pretend for a second that we know which constraints are active, and by active I mean strictly here, and which constraints are not active by exclusion. So I know by A is a set of indices, right? It's maybe constraint 1, 11, 15, 21 are active, right? And when I note something like this, I'm basically extracting constraints, the constraints that correspond to these indices from H. Does it make sense, this notation, or is it clear? Okay. So if I focus on the strictly active constraints, here is what the equations become. So the mu's corresponding to these constraints will be non-zero. So I will be interested in this product to all the constraints that are strictly active. And for the strictly non-active constraints, the mu's will be 0. So I can dismiss the inactive constraint from that product here. It's maybe not completely obvious, but hopefully it makes sense to think that, right? So is that, should I detail that, or is it? No, it's okay. Maybe this one is easier to understand. I have this inequality constraints. If your constraint is strictly active, that means the corresponding line in this equation equals 0, right? So I can write that on the strictly active constraint, these guys will be 0. And the inactive ones, this will be less than 0 strictly, right? But the bottom line is, if you know the active set A, you can write a bunch of equations that define a lot of things that are purely equality equations. So the mu A's, the mu corresponding to the active constraints, are strictly positive, and the A bar, that's all the indices corresponding to inactive constraints, they are strictly less than 0. I can rewrite this set of equations in a matrix form, and I end up with something that looks like something we've seen before. It's kind of always the same form: Hessian, constraints, gradient here and here. And here I'm only putting in the active H's. So this thing here, if A changes, it will change size. And same here, right? And this mu A will also change size. Okay, what's going to happen now is, if I know A, I can form this linear system, solve it, and I know my primal draw variables. Why? My delta W is given. As long as this matrix is full rank, I can solve that. Delta W is given as my primal variables. Lambda is given. I get my mu A's, the mu's matching the active constraints, that are non-zero. And I know that the mu A bars, the inactive mu's, they are 0. So I can basically know all my variables from that. Does it make sense? So if I know A, I can form that system, compute my solution. And the QP is solved, right? I have found the delta W's and also the mu's and lambdas that satisfy my KKT conditions. So essentially, as soon as you know the active set, solving the QP boils down to one linear solve. So the idea of active set methods is find the active set, and then you're down to solving this linear system, and the QP is done. This matrix, as usual, very structured. That's block diagonal, banded, and block diagonal as well. So this is fairly cheap typically to factorize this system, if you do the right thing. So checking an active set, that's also an important thing. Checking an active set takes only solving this system. Why? You can guess your active set, form the system, solve for delta lambda, delta W and lambda, and mu A. And then you can check these two things. Are my mu A strictly positive? And once you get your delta W, you can check that as well. Form nabla H A bar transpose times this guy plus this guy. Is that less than 0? If this holds, then your active set is correct. If you find a mu A that has the wrong sign, or if you find some constraints that should be inactive but they end up being active, then you know that A cannot be correct. Does that make sense? So you can guess A and check in one linear solve if this A is correct or not. And that's pretty much the idea of this active set methods. You essentially will guess an active set and check if it's correct. If it's not correct, you'll change it. So I'll show you how it works after break.